This is Lecture 2 in Module 8 from the book Problem Solving Guide for Mechanics and Thermodynamics. The subject is moment of inertia. The mass of an object, one way to determine it, is to push on it with a net force and see how much it accelerates. If you push hard and there's not much acceleration, it's a big mass. If you push and the mass takes off, it's a small mass. Mass can be thought of as the resistance to acceleration. Another word that describes this is inertia. In rotational motion, the analogy to mass is moment of inertia, I. So when we look at rotational motion, instead of putting in the mass, we're going to put in the moment of inertia. As we'll see, it matters where the mass is, not how much the mass is when you want to spin something. The moment of inertia of an object can be determined by just torquing it and seeing how much it accelerates. If it starts to spin fast, the moment of inertia is low. If you put a torque on it and it has a very small angular acceleration, it must have a big moment of inertia. So moment of inertia is the resistance to angular acceleration. Mass is the resistance to linear acceleration. So the rotational analogy of F equals ma, instead of the force, we have the torque. Instead of the mass, we have the moment of inertia, I. And instead of the linear acceleration, we have the angular acceleration. So the sum of the torques is I alpha. In the previous module, the sum of the torques was always 0. But here it's I alpha. There are a bunch of formulas for moments of inertia of different shapes, but to really understand the concept of moment of inertia, it's best to see where it comes from. So we have a solid disk spinning around at angular speed omega. Radius r, mass m. How much kinetic energy does it have? We've seen previously the kinetic energy of a mass m moving at speed v is 1/2 mv squared. The problem here is that the outside of this thing is moving faster than the inside. Inside's moving slow. Outside's moving fast. So what speed do we plug in? So we're going to think of the disk as an infinite number of infinitely small masses. We're going to divide it up into an infinite number of pieces, and we're going to calculate the kinetic energy of each piece, and we're going to sum them all up. Here's a piece right here. We're going to call that dm. How fast is dm going? We need the speed of dm to get the kinetic energy of dm. So what we're doing is we're making this mass so small that all of it's moving at the same speed. You say, well, the outside's moving a little bit faster than the inside. I said, no, it's dm. It's infinitesimal. It doesn't have an inside or an outside. Dm is not a mass, it's an idea. Infinitesimal. So what we're going to do, the kinetic energy is the sum of all the kinetic energies of each piece, which is 1/2 dm times v of dm. V squared of dm. Now we're going to have to write dm and the speed of the dm in a way that allows us to perform this sum. So for the mass, it's pretty simple. The mass of the whole thing, big M, divided by the area of the whole thing, that's the density, which is conventionally called sigma for areal density, mass per unit area. And that's the same as dm over A, over dA, where dA is the area of this piece right here. That's the density, mass over area. It's constant. It's uniform disk. So there's dm. In polar coordinates, dA is dr rd theta. And we can see that by looking at the two sides of this box. Here's dr, small piece of the radius, dr, and then we have this side, which is rd theta. And we can get that from the definition of the angle. D theta is some infinitesimal angle. That length is rd theta. So it's a box, length times width, dr times rd theta. And that's what we have for dA. The speed depends on how far it is away. Let's define the distance from the middle as r. So let's put r on the diagram. And the speed of this piece is omega r. Omega is the same for every piece in there. The speed is not. The speed is omega r. All right, so now we're pretty close. The kinetic energy is 1/2 dm, that's dm, m over a dA, times the speed. The speed's omega r. This is true for every piece on there, every dm on there. The 1/2, the m, the a, the omega squared, those are all constants. We can factor them out. And we have this. We can pull this constant outside the integral sign. And we have r cubed dr d theta. Integral of d theta is 2 pi all the way around. Integral of d theta is theta and then goes from 0 to 2 pi. R cubed dr is r to the 4th over 4. That goes from 0 to r. And if you don't know it, you can just ask Alexa. Hey Alexa, what's the integral of r cubed dr? Alexa will tell you. So here's the result. There's the theta integral, there's the r integral. And we substitute in pi r squared, it's a circle, for the area of the disk. And we get the kinetic energy of a disk of mass m, radius r, rotating at omega is 1/4 mr squared omega squared. We can't use 1/2 mv squared because all of the speeds are different. The general formula, the rotational analogy for the kinetic energy of a spinning object is 1/2 I omega squared. Right? Instead of 1/2 mb squared, it's 1/2 I omega squared. So we can set our result 1/4 mr squared omega squared equal to the general formula and pull out the I. So the omega squareds cancel. I got a 1/4 and a 1/2. That makes a 1/2 over here. So I is 1/2 mr squared. The moment of inertia of a disk is 1/2 mr squared. Another way to think about the mode of inertia of an object is it's a measure of the amount of kinetic energy it has when it's spinning at omega. If two things are spinning at omega and one has more kinetic energy, it has more inertia. If you understand the concept of moment of inertia, you should be able to just write down the moment of inertia of a thin hoop. Mass m, radius r about its major axis. So here's a thin hoop spinning around. What's its moment of inertia? You thinking about it? You can pause the video. I'm going to show you. Spoiler alert. When a hoop of radius r is spinning about its major axis with angular speed omega, all of the mass is moving at omega r. Right? All of this mass is moving at v, which is omega r. So the kinetic energy is 1/2 mv squared because all of the mass is moving at v. You don't need to integrate. If we set this equal to 1/2 I omega squared, we get that the mode of inertia is mr squared, which you probably knew already because all of the mass is r away. So the mode of inertia must be mr squared. The reason why this is 1/2, the moment of inertia of this, is that the mass in the middle just isn't moving very fast. Here, all the mass is moving at v. What about a solid sphere? Let's think about that. Where would the moment of inertia of a sphere rank among a hoop and a disk? We know it's less than the hoop, okay? The hoop is mr squared because all of it's r away. Where is it between a hoop and a disk? Is it in between, above, below? In other words, if you had this, if I put a torque on these guys, I wrapped a string around the middle and pulled on them, which would be harder to accelerate? What do you think? If each of these were spinning at omega, which would be harder to stop? Which has more energy? That's a direct measure of the moment of inertia. Another way to think about it is to have a race down an inclined plane. Each has mass m, radius r. The gravitational potential energy is the same. They're released from the same point on the plane. They don't slip, they roll, so we don't have any thermal energy generated, no grinding along the surface. At the bottom, each must have the same kinetic energy because each had the same gravitational potential at the top. The object that has more rotational kinetic is going to have less translational kinetic, and it's going to lose the race. High inertia objects are hard to spin, so they're going to lose the race. Let's watch the race. Who's your money on? Did you see it? Hey, we need to have a photo finish. Sphere's first, cylinder second, and the hoop is a distant third. The moment of inertia of a sphere about a diameter is 2/5 mr squared. And if you do integrals in spherical coordinates, you should be able to bust that out. For comparison, as we've seen, the cylinder disk is 1/2 mr squared. So this is 5/10 mr squared. That's 4/10 mr squared. They're pretty close. The hoop is much bigger, mr squared. Wait a minute. I know you're thinking here, what about F equals ma? All three masses have the same m. They have the same radius. They're at the same place on the plane. The force down the plane is mg sine theta. Here's the object. There's mg. This is theta. That's mg sine theta. The force down the plane's all the same. How can the accelerations be different? What's up with that? Figure it out. Think about it. Great opportunity to develop your mind. Pause it and think. Get a friend. Talk about it. What's going on here? Come on. If the incline was frictionless, all three shapes would have the same acceleration. But it's not frictionless. If it was frictionless, they wouldn't spin. The shapes are rolling without slipping. In order to get them to roll, there has to be a torque on them. And that torque is from the frictional force. And here's the frictional force right here. The torque is Rf, and that's causing the alpha, the spin, to increase. A larger torque is needed to spin the hoop because it's harder to spin the hoop. It has a higher inertia. So the frictional force on the hoop is bigger up the plane. So the net force down the plane is mg sine theta minus the frictional force. The bigger the frictional force, the less the acceleration. F equals ma is still valid. You just have to include all the forces. And there's a frictional force there. If there was no frictional force, they wouldn't spin. So friction slows the ball down, produces a torque that causes the object to roll. And once it's rolling, it's sapping the translational kinetic energy. In bowling, it's the translational kinetic energy of the ball that knocks down the pins, not the rotational. So the goal is to get the ball to the pins with the maximum translational kinetic energy. To do that, they put oil on the lanes. The lanes are very slippery, so the ball doesn't roll without slipping. The ball keeps its translational kinetic energy. It doesn't give it away to rotational kinetic energy. And as you know, when you're bowling, it's not a good idea to go into the lane because it's very slippery. For a very nice problem involving bowling, check out problem 820 on page 268 of your textbook. In fact, all four soul crushers are a terrific opportunity to build your brain and become a better problem solver. Don't worry about getting the answer. The answer is not important. Just think about them really hard. Here's another one to think about. When tall smokestacks are demolished, they almost always crack in the middle on the way down. Here's an example. I can never tell if it's going or not. Is it going? Ah. See it? It's going. And they almost always crack in the middle, right there. See the crack? It broke. It broke in the middle. To discover why, calculate the acceleration of the end, the high end here. So it's a falling rod. How fast is this guy accelerating? Not the angular acceleration, the linear acceleration, and compare it with g, the acceleration due to gravity. That's lecture 2.